Okay, so it's my pleasure to welcome Melissa Sherman-Bennett from MIT. She's going to talk today about cluster structure on braid varieties.
Yeah, so thanks so much for the invitation, and sorry that I can't be there in person. I hope the talk is okay anyway, and I'll try to remember to stop for questions and really give you time to come up to the computer and say them, but if I forget, just call me out. Okay, so as Scott said, today I'll talk to you about cluster structure on braid varieties. So this is joint work with Pasha Galashin, Thomas Lam, and David Speyer. We have a couple of papers up on the archive. The first one is type A, the second one is general type, so you can find more details there. My slides are also on my website. Okay, so I'm going to start out by telling you a bit about braid varieties, which are some affine varieties. I think they're very nice. And then I'll spend most of the talk telling you about a particularly rich combinatorial structure that their coordinate rings have. So this is called the cluster structure, and I don't expect you to know at all what those words mean. I will tell you through the course of the talk. Okay, so first, to tell you about braid varieties, I need a little bit of background about flags. So in the context of this talk, G is going to be a complex simple algebraic group. I'm going to choose some favorite Borel B inside of G. B minus is the opposite Borel. And of course, W is the Weil group of G. And nothing will harm you in this talk if you just spend the whole time thinking about type A. I'll try to put things that are sort of type A in blue. So if you decide to think only about type A, then G is SLNC. My favorite choice of Borel is the upper triangular matrices, and the opposite Borel is the lower triangular matrices. And the quotient G mod B is naturally isomorphic to the complete flag variety. So just a quick reminder, points in here, they're chains of subspaces, so flags of subspaces, V0 contained in V1, contained in V2, etc. So that Vi has dimension I. Okay, and over the course of the talk, I'll be talking about G mod B more generally. I'll still call it the flag variety even when G isn't SLN. So another important thing about G mod B to remember through the course of the talk is that it has two very nice and very well-studied decompositions. The first is into B orbits. So those are called Schubert cells. They're indexed by elements of the Weil group. And the other decomposition is into B minus orbits. Those are called opposite Schubert cells. Pieces are still indexed by elements W in the Weil group. Okay, so this is all kind of classical. To define braid varieties, I'm going to need a little bit of notation. So, and then I'm also going to need the notion of relative position of two flags. So if I have two flags, F and F prime, I say that they're in relative position W if the kind of the ratio of these two flags sits inside of a particular B orbit. So if you haven't seen this before, really you actually only need to think about two kinds of relative position. So the first is when two flags are in SI position, where SI is one of the generators of W. And okay, this one is actually easiest to think about in type A. So in type A, two flags, like two honest flags, are in relative position SI if they differ exactly in the I-dimensional subspace, right? So these two lists of subspaces are almost the same, they only differ in the ith spot. Okay, and you can kind of imagine what this notion should be in other types. And the other kind of relative position that I need you to remember is this kind. So I've got a particular, my flag on the left is a particular flag, W naught B, which I'm going to denote by F minus. This is the anti-standard flag. And if I'm talking about the relative position of F minus and another flag, that relative position here, it's actually just recording which opposite Schubert cell my flag F is in. So when you see this notation, just think, oh, we are recording somehow the opposite Schubert cell that my flag F is in. Okay, so let me pause for a second. Are there any questions? All right, looks like no, so I'm going to keep going. So with that bit of notation, we can define braid varieties. So my braid variety is indexed by a pair. The first element of my pair is, I'm going to denote it by beta underline. And this is just going to be a word in the simple transpositions of W. So it doesn't need to be a reduced word. It's any word at all. And then the second element of my pair is an element of my vowel group, so some U in W. And I just need to be able to find this element U inside of beta underline somewhere. So beta underline should contain a reduced expression for this U. Okay, and with that, we can define the braid variety X beta underline U. Points in here, I like to think of them as walks in my flag variety. So a point in X beta underline U is a walk in the flag variety, which starts at B, so starts at the standard flag. And then I'm going to take steps dictated by the letters of beta underline. So my first step is in direction SI1. So if I were in type A, to pass from F1 to F2, I would just be changing the I1th dimensional subspace. And then my second step is in direction SI2, where that's like the second letter of my word, and so on. Okay, so that's how the data of beta underline plays a role. It's going to tell me which direction I need to step during my walk. And then where does U come in? Well, U is going to constrain where my walk ends. So what the final flag in my walk is. Well, U is in particular going to tell me which opposite Schubert cell my final flag lives in, right? So that's what this notation means. It means that my final flag is in the opposite Schubert cell indexed by the permutation U. Okay, and there's another way to think about this, which is that if you just think about these walks in direction, like where you take steps according to the word beta underline, this is what's called an open Bott-Samelson variety. So here I'm not constraining at all where my walk ends. There's a natural map from the open Bott-Samelson into G mod B by just projecting onto the final flag. And my braid variety X beta underline U is the fiber of this natural map mu over the opposite Schubert cell indexed by U. So that's another way to think about it. And these varieties have been studied under in a couple of different contexts. So Escobar called them brick varieties. She was actually interested in the closures of these braid varieties. Mellett studied them in the context, I think, of character varieties and didn't call them anything at all. And then Casals, Gorsky, and Simmental kind of studied them and called them braid varieties and sort of defined them kind of in exactly this way. And so I'll be using their notation. Okay, so looking at this, you might be thinking, well, why are they called braid varieties? I don't really see any braids at all. The reason for this is because if the word that you use to define X beta underline U, so if the beta underline is related to another braid word, gamma underline, by some number of braid moves, then the two braid varieties will be isomorphic. In a very, well, I hesitate to say canonical, but a very natural way. So what that means is that instead of keeping track of the word beta underline when I'm thinking about this variety, I can just think about an equivalence class of words all related by braid moves, and all of those words will encode the same geometric object. So that equivalence class of words under braid moves is called positive braid, an element of the positive braid monoid. So that's what I'll be using to index my braid varieties from now on. So I'll write X beta U, where beta is some element of the positive braid monoid. Okay, so what can I tell you about these braid varieties? Well, actually, maybe before then I'll stop to make sure that the definition is clear.
I have a question.
Yeah.
In Escobar's situation, are these still isomorphic if you take the closures?
I believe not. Yeah, so Escobar was studying the closures of these braid varieties inside of the closed Bott-Samelson, and I believe that once you take closures, they're no longer isomorphic. Yeah, that's a good question. Any others? Okay, So, okay, so now what can I tell you about these things just right off the bat? Well, they're smooth, they're irreducible, they're affine, and they have a very predictable dimension. It's just the length of the braid word that you picked minus the length of U as an element of the file group. And you might be thinking, well, okay, fine, like you can define these. It turns out that geometrically they're fairly well behaved, but kind of why would you do this? Well, our main motivation were some special cases of braid varieties that we were kind of already interested in. So if you choose your word beta underline to be a reduced expression for some element V of the file group, it turns out that the information of this whole walk of flags is actually contained in the final flag. So in this special case where this word on top is a reduced word, in fact, you only have to remember the final flag and that will determine everything. So what this means is that the braid variety in that situation is isomorphic to just a subset of G mod B, and it's this subset. It's the flags which are V related to the standard flag and W naught U related to the anti-standard flag. And if you think about this a little bit, you can see that this is actually a very natural subset in terms of the two decompositions of the flag variety. It's just a Schubert cell, the one indexed by V, intersected with an opposite Schubert cell, the one indexed by U. And this kind of intersection, it's sometimes called an open Richardson variety. It is independently of interest. So Deodar maybe was the first person to think about these. He used them to compute R polynomials, which are related to Kazhdan-Lustig polynomials. And open Richardson varieties also arise really naturally in total positivity, work of Lustig and Reach. So that's one reason to care about braid varieties, is they generalize open Richardson varieties, which are themselves of interest. Okay, and then in type A in particular, if you choose your word beta underline to be reduced, and you choose it to be even more special, you choose it to be a reduced expression for a permutation with a unique descent, then it turns out these braid varieties are really very nice. They're isomorphic to something called an open positroid variety. And I won't get too much into what these are, but there's a lot of really nice combinatorics around open positroid varieties, a lot of it developed by Postnikov, follow-ups by Lam and Speyer. And one really nice, kind of the nicest case of this example, or the most straightforward case, is called, well, it's basically just the Grassmannian GRKN. It's a little bit smaller than that. It's the Grassmannian take away a divisor. But this is just to say, if throughout this talk it feels a bit too abstract, you can just think about, like, in the background, we have something that's just as straightforward as the Grassmannian. So that's one of the kind of spaces I'm talking about. Okay, so that's braid varieties. And now, okay, so let me tell you just first what our result is, and then I will demystify it. So I promised that I would tell you about this very nice combinatorial structure on the coordinate ring of braid variety, which is, so our result is that these braid varieties, their coordinate rings are what are called cluster algebras. And okay, I'll tell you what cluster algebras are in a second. For now, just know that they are some commutative rings that are defined by a very small piece of combinatorial input called a seed. So what our result is we start with our favorite braid word beta underline, permutation U, and we give an explicit construction for this combinatorial information, this seed. And then we show that the algebra generated by this combinatorial information in an algorithmic way is exactly the coordinate ring we're interested in. And in type A, we can kind of beef up our combinatorial, like our explicit construction of this combinatorial data, and we have a nice bicolored graph sitting in the background that's controlling everything. Okay, so that's where I'll get to in the rest of the talk. Before I continue, let me just give you some context. So there's related work of Casals, Gorsky, Leshan, and Simmental. So they independently give a construction or they independently show that this coordinate ring is a cluster algebra. They use very different combinatorics from us. The seeds, this bit of combinatorial input that they produce is quite different. Yeah, so it's not clear how the two results are related. This result also resolves a conjecture of Leclerc from 2014. So he was just interested in the Richardson case. So when beta underline was reduced, and he conjectured that in that situation, the coordinate ring is a cluster algebra. This result also generalizes the work of a handful of other people who sort of dealt with various special cases of braid varieties. And I should also mention that our approach owes a big intellectual debt to Ingermanson, who is a PhD student of David Speyer's. In her thesis work, she had some results in the Richardson case, which really inspired us. Okay, so now that I've given you this fairly mysterious theorem statement, so I've told you what braid varieties are, but I haven't really told you anything else. Let me demystify it and tell you about cluster algebras. Oh, sorry, before I do that, let me give you a corollary, which is only in type A, but very interesting nonetheless. So as a result of knowing that this coordinate ring is a cluster algebra, in type A, if you look at the finite field point count of one of these braid varieties, what you obtain is a certain a piece of a certain link invariant, of a link that you build out of the data of U and beta. So yeah, I'll just leave that as in type A, there's some very interesting and somewhat mysterious connections to knot theory which pop out. Okay, so now let me tell you what a cluster algebra is. Okay, so these were introduced by Fomin and Zelevinsky around 2000. They were very interested in total positivity and Lustig's dual canonical bases. They were trying to give sort of a framework that systematically explained some of the combinatorics in algebra beneath these two things. And so, okay, so what is a cluster algebra? Well, it's a commutative ring, but unlike usual, when like to describe a commutative ring, usually I would give you a complete set of generators, usually finite, and a complete set of relations among those generators. But for cluster algebras, instead, what I'll do is I'll hand you a very small number of the generators and a little bit of extra combinatorial information. That together is called a seed. And then I'm going to give you a way to grow the rest of your algebra from this seed. Okay, so, right, so I said, okay, so what is a seed? Well, it's a pair. The first element of your pair is this little subset of your generators. So it's a tuple of polynomials or rational functions. I call all of the rational functions in this seed a cluster variable, and the tuple of them is called the cluster. Okay, so that's some algebraic information. We have some functions. And then we also have some combinatorial information, which is a directed graph, also called a quiver. And together, these two pieces form a seed. So here's an example. So in this case, my cluster variables are A, B, and C. The cluster is all three of them together. And the quiver, the directed graph, is the one that's shown here. Right? And I should have said, I think of my cluster variables as being the vertices of my quiver. So the arrows go between cluster variables. It's important that the cluster consists of algebraically independent functions. There's also a small technical point, which is that some of the cluster variables are declared to be frozen. So I'll denote those with sort of these little ice cube, these blue boxes, vertices of the quiver. So that means that like B and C are frozen variables. Okay, so someone hands you this little snippet of algebraic information, the functions, and combinatorial information, the quiver. And from there, there is a process called mutation to produce another seed. So this mutation, you can perform it at any non-frozen vertex of your quiver. So in my example, I only have one non-frozen vertex. It's A. So the only mutation I can do is there. And what mutation will do is it will change the quiver a little bit around wherever you mutated in an algorithmic way. I'm not going to go through it now, but it's completely determined. And it will also change the cluster it will just replace whatever cluster variable was sitting where you mutated with a new one. So since I mutated at A, in my mutated seed, I'm going to get a new cluster variable sitting here. And what is this new cluster variable? Well, it's completely determined by the neighborhood of my mutated vertex in the quiver. So I'm always going to put like my old cluster variable in the denominator. So I have this A in the denominator. And then what goes in the numerator? Well, two terms. One term records the cluster variables pointing into A. That's B and C. And the other term records the cluster variables pointing out of A, and there are none of those, so my term is 1. Okay, so someone hands me this seed. Now you can pick any non-frozen vertex, and you can mutate. You'll get a new seed with new cluster variables and a new quiver. And then you can pick another vertex and mutate again. You just kind of keep mutating in all kinds of ways. And that process, so starting with the seed and performing arbitrary sequences of mutations, that gives you all of the cluster variables, which will be all of the generators of your algebra. So your cluster algebra, the cluster algebra from sigma, the seed sigma, is polynomials in all of the cluster variables you see in all of the seeds you get by mutating sigma in any way you want. And we also throw in the inverses of the frozen variables. Okay, so in this particular example, so when I started with this seed, so I had this seed and then I mutated to get this one. It turns out that mutation is an involution. So if I mutate again, I just get back here. So these are the only two seeds I see. And that means that my cluster algebra is generated by all of the variables I see in either of these two seeds. So A, B, C, and BC plus 1 over A, together with the inverses of the frozen ones. So I also throw in B inverse and C inverse. Okay, so that's my cluster algebra. And I told you I was going to talk about coordinate rings that are cluster algebras. So if you look closely enough at this example, it is the coordinate ring of something. And that something is, well, maybe it's easier to see if you sort of ignore the inverses here. So if you ignore the inverses here, we've got a ring generated by A, B, C, and another generator. So maybe this generator called D, which satisfies AD minus BC equals 1. So what is that? Well, that's nothing more but the coordinate ring of SL2. So because in the cluster algebra, I also throw in the inverses of B and C. This whole cluster algebra is the coordinate ring of something a little bit smaller than SL2. It's the coordinate ring of SL2 circ, where the circ just means I take away the divisor where BC equals 0. Okay, and so in this circumstance, when in this circumstance, we say SL2 circ has a cluster structure, meaning its coordinate ring is a cluster algebra. Okay, so that was a lot of information. I'll pause here in case anyone has any questions about the definition of a cluster algebra.
I understand why that's AD minus BC equals 1, but when you write it as BC plus 1 over A, it looks like A can't be 0. So I am not quite sure why in the end
Yeah.
A would be 0.
Right, so when I write it this way, this is actually leads right into my next slide. When I write it this way, what I'm doing is I am telling you actually a bunch of tori in my variety, which cover up to codimension 2. So if I only care about coordinate rings, I can kind of fill in some stuff in higher codimension, and that's how I'll get SL2 circ.
Okay, thanks.
Yeah. Yeah, so if you're a geometer, maybe a more natural way to think about this. Okay, so as I said, you have a cluster structure. Some affine variety has a cluster structure if its coordinate ring is cluster algebra. But maybe a more natural way to think about this, if you like geometry rather than algebra, is that actually each one of your clusters that you've produced by mutation, it's going to give you a torus, an open torus sitting inside of your variety. And so what is that torus? Well, okay, the torus indexed by a particular cluster by a particular seed, that's just all of the points in your variety where your cluster, the cluster variables in that cluster are non-zero. Okay, and I'm asserting that this set will actually always be a torus. It's not obvious from what I've told you so far. So having a cluster structure means that your variety contains all of these tori, and in fact, they cover up to codimension 2. And in this perspective, and maybe you want to think about the tori as being kind of the more fundamental objects. So they're the things that are actually like sitting inside of the variety. So if someone hands you one of the cluster tori, if someone hands you one of the cluster tori and you want to recover the cluster, well, what you're really doing is you're picking a distinguished basis of characters of your torus. And you kind of need to pick them carefully because you want to pick a basis of characters for each of your tori, and you need the bases to be sort of compatible. So yeah, each cluster gives you a distinguished basis of characters of your torus, and then you're sort of choosing them all at once so they're compatible in some nice way. And your quiver is just now encoding some relations on your variety, and it's really encoding the change of basis between tori. And so, okay, if your tori are very close together, maybe your quiver is sort of directly encoding this. If they're far apart, you might have to do lots of mutations to get from one to the other, but kind of all that information is still in one quiver. So from this perspective, from this perspective, in the example of SL2 circ, we have 2 cluster tori. The first one is where A, B, and C are non-zero. So that was like the variables from my first seed. And then the second one is where B, C, and D are non-zero. So that's the variables from my second seed. And this is maybe the perspective that I'll take for the rest of the talk is we're actually going to start with the tori, and then we're going to try to simultaneously pick these bases of characters very carefully, and then we'll find the quiver in exactly this way. Okay, so that's what having a cluster structure means, but why care? Well, under some kind of reasonable assumptions on the cluster algebra, if your variety has a cluster structure, then it automatically endows the coordinate ring with a very nice basis, sometimes called the canonical basis, which has positive structure constants. And okay, this is a very major result in the field due to Gross-Hecking, Kiel, and Kinsevich. This also kind of is why cluster algebras are defined the way they are. They're sort of defined so that you get your hands on as much of the basis as possible from the beginning. So each one of the cluster variables will be part of this basis. So will products of cluster variables in the same cluster. Another reason why you might be interested in cluster structure is there are some, like as soon as you have a cluster structure, you have access to some fairly natural partial compactifications or complete compactifications of your cluster variety. You also get valuations and torque degenerations of those compactifications. There's also some results on the cohomology of a variety with cluster structure due to Lam and Speyer. In particular, a curious Lefschetz property holds. So those are some reasons why you might care about this. Another one, which maybe which I didn't write down but I should have, is that, as I told you, cluster algebra structure, I mean, there's a lot of rich combinatorics there. So you're sort of grouping functions together into these clusters. The quiver itself has a lot of nice combinatorics. And so as soon as you have a cluster structure, that means that there's lots of very interesting combinatorics to investigate. And that's hopefully what I'll kind of show you by the end of today's talk, some of the really nice combinatorics that's hiding in here. Okay, so now that you know what a cluster algebra is, let me say the result again. So we pick our favorite Braid variety, X beta U, and we pick any word for beta that we want, so any beta underline. So what we do is we give an explicit construction of a seed, so some functions on the Braid variety and a quiver, and then we show that, yes, indeed, the coordinate ring is the cluster algebra corresponding to that seed. And okay, so we have this construction in general type. In type A, there's some more combinatorics, as is usual in type A. And where that comes in is in the quiver Q. So In general type, we have a way to construct the quiver. We have an algorithm. In type A, there's just a bicolored graph sitting in the background, and the quiver can be read off of this bicolored graph in a relatively straightforward way. Okay, so what I will tell you about today concretely is for each braid word beta underline, I'll find you an open torus sitting inside of the braid variety. And then I'll tell you how to pick this nice basis of characters for the torus for each one of them. And then I'll be a little bit vague about the quiver in general, but it is determined by thinking about how to go between these two tori and how these nice bases that we chose for both of them are related. So that going from this torus to this torus, that is going to determine what our quiver will look like. And it will also determine what this bicolored graph is. I'll talk more about that later. Okay, and then once we have these tori, what you do is you use mutation to get infinitely more tori, and you show that these actually cover x beta u. And yeah, so I won't really tell you much about the proof. I'll just sort of outline the beginning steps, like how do you see the cluster structure? Okay, any questions?
But it's not enough. So what's interesting, I guess it's interesting you get infinitely many tori, like you would think you might get all just the tori that would correspond to the different words would be enough.
Yeah, that's right. So it's, I mean, for the proofs, it's enough to have the tori for each word, but to actually cover up to codimension 2, you need infinitely many usually. And it's just, yeah, this is like a funny feature of cluster algebras. It's also true that like cluster algebras are usually finitely generated, but the cluster algebra procedure produces infinitely many cluster variables that you're going to use as generators. So there also, it kind of feels like you do something that's a little bit overkill, like a little bit more than you need to. Yeah. Anything else? Oh, I thought I heard something, but maybe I didn't.
No, I just say that's that. Yeah.
Okay. All right. So let me tell you about these tori. Okay, so I'm going to fix forever now my beta and u, and now I'm also going to pick the braid word beta underline. And I'm going to produce for you one torus for each of these beta underlines, and I'm going to call them Deodar tori because they're really very much inspired by Deodar's decomposition of Richardson varieties. So yeah, they sort of come kind of straight from something that Deodar was doing in the 80s, I think. Okay, so remember, points in my braid variety are walks in the flag variety, right? They're walks that look like this. And so all I've done, right, so there are points where I've specified what steps I've taken in my walk, and I also specify the opposite Schubert cell that my final flag is in. So to describe the torus, what I'm going to do is I'm just going to constrain the opposite Schubert varieties, opposite Schubert cells that all of the intermediate flags in my walk are in. So, so the informal way to say this is you're a point in the torus if when you look at the end of the walk and go backwards, in each step backwards, you're going to greedily increase your distance from the anti-standard flag. Okay, so what does this mean? Well, okay, so say I'm starting at my final flag and I'm stepping back. I know which direction I'm taking the step in. And it turns out that in this situation, so I know this distance and I know this distance, there aren't very many choices for what this distance can be. So if this distance is v and this one is si, the only choice for this distance here is either v or vsi. And to be in the torus, I'm just going to demand that I choose the larger of these two permutations each time I step backwards. So just to do a quick example, in type A, so say this is my walk, and my constraint is that my last flag actually is f minus. So if I'm going to be in the torus, when I take this step back, okay, so I need to greedily increase my distance from the anti-standard flag. So my options for this arrow, the label here, is either the identity or SI. And to be in the torus, I need to pick the bigger of those two. So the bigger of those two is SI, S1. Okay, and then I can take another, when I take another step back, my options for this arrow are either whatever's here, S1, or whatever's here times this S1. So it's S1, S1. So my options are either S1 or the identity. I have to pick the bigger one. So that means that this is also an S1. Okay, and then going back here, my options for this arrow are either S1 or S1 times S2. S1 times S2 is bigger. And then here on this arrow, I can either see S1, S2, or I can see S1, S2, S1. That one is bigger, that's W naught. So here I see W naught, and then I'll be W naught forever because I can't, I have to really increase my distance. That means I can't go down. Okay, so that's what my torus looks like. It's all of these points, right? All of the walks which fit into a diagram like this, where these labels are determined by a greedy procedure. And I'm not going to tell you why it's a torus, but it's basically it's a torus because at each step I did this greedy thing. And that turns out that's the generic choice. So it'll kind of produce a C star in many situations. Okay, so now a little bit of terminology. So so this is what my torus is, and now I want to tell you about this distinguished basis of characters. And I need to index them by something, so I'm going to introduce some terminology so I can index this basis of characters. So in my torus, I see two kinds of little triangles, right? And inside of this picture, I see two kinds of little triangles. The first kind is when I see the same permutation on the right and left edge. And the second kind is when I see different permutations on the right and left edge. Okay, so if I see the same permutation, I'm going to call that index a solid index. And if I see different permutations, I'm going to call it a hollow one. The idea here is that the hollow indices are not important. They will not index they will not index a character. The solid crossings or the solid indices, those are the dependable solid ones, they will index by basis of characters. And okay, if you don't want to do this whole thing where you fill out this little grid of triangles and then decide what's solid or hollow, there's actually an easier way to figure out solid and hollow. The hollow indices just form the rightmost sub-expression for whatever your permutation U was. So in this example, my U was W naught and S3. So the rightmost sub-expression inside of this word for W naught is this one. So these are my hollow crossings, and the other ones are solid. Okay, and so because of this, we have just the right number of solid crossings. We have length of beta minus length of U many. So that's the dimension of my Braid variety. It's also the dimension of this torus. So I'm going to use these solid indices or solid crossings to index my cluster variables. Okay, so now what are these cluster variables? Well, geometrically, they're pretty straightforward, or like the idea of them is pretty straightforward. So to figure out my cluster variables, what I'm going to do is I take my torus and I look at its complement in the Braid variety. So its complement will decompose into a union of irreducible hypersurfaces, which I'll call Deodar hypersurfaces. And roughly speaking, these Deodar hypersurfaces correspond to walks where you make one mistake in this greedy procedure of picking permutations on the arrows. And I'm not going to go into more detail, but so it's relatively easy to describe the points in these Deodar hypersurfaces. And our cluster variables are just going to be, well, the functions that cut out the Deodar hypersurfaces. So if C is some solid crossing, it corresponds to a Deodar hypersurface BC, and then the corresponding cluster variable XC is going to be, well, a particular torus character, which vanishes to order 1 on that Deodar hypersurface and does not vanish at all on the other Deodar hypersurfaces. And this is a little bit vague. It might feel like these aren't well defined. Don't worry, we do have this is sort of like the easiest way to think about them, but don't worry, we have a more rigorous way to define them as well. And I should also warn you, this story is a little bit of a lie. There's some technicalities for the frozen variables, but this is a sort of intuitively exactly what's going on. Okay, so this is the tori, and these are the cluster variables that we pick. I'm about to transition into talking about like the type A combinatorics of the quiver. This is a good time for questions about this part of the construction. All right, I will keep going. So that's the geometric stuff. So we have all of these tori. We've got some like pretty natural characters on those tori. Those will be our cluster variables. And in principle, at this point, you're done, because now that you've picked your basis of characters, I mean, it's sort of, if you're going to get a cluster structure at all, this has to determine the quiver. So the rest of this, like once you've picked the right cluster variables, everything else is determined by what you already know about the geometry. Of course, this is in principle. In practice, it's actually can be quite difficult now to figure out what the quiver is. Yeah, so I'll say in general, basically the way you figure out the quiver is, well, you have these braid moves, and on your word beta underline, and it induces an isomorphism between braid varieties. And each one of these, like x beta underline u and x beta prime underline u, they both have a Deodar torus sitting inside of them. And so to determine the quiver, what you need to answer is, well, how are the special characters that you picked here, if you pull them back, how do you express them in terms of the special characters here? And well, this is a little bit complicated, but they satisfy something that's close to some classical determinantal identities. And sort of you can use this plus induction to determine the entire quiver. Okay, so I'm intentionally being vague about this. I will also intentionally be vague and say we have a root theoretic algorithm for this quiver. So it is something that you could ask a computer to calculate. In general type, it's fairly complicated. Like the computer is a bit slow to compute this, probably the fault of our algorithm and not actually the fault of the quiver. But in type A, you can be sort of much more explicit and just give a recipe for the quiver without doing anything like particularly algorithmic or particularly inductive, anything like that. So I'll spend the remaining last little bit of the talk talking about what to do in type A to get the quiver. And it's all just combinatorial. So the big picture idea is you start with your beta underline u. So you already know your torus and your cluster variables. And now to get the quiver, what you'll do is you'll take this beta underline u and turn it into a bicolored graph. And then each solid crossing of beta underline, each solid index, so each one of your cluster variables, you're going to represent it with some cycle in your graph. So you're just going to draw a cycle in your graph. And the interactions of these cycles in your graph will determine the quiver. Yeah, so you can stop at this point and just say, okay, like now that I have the cycles, I can draw the arrows of my quiver in some way, or you can upgrade it a bit. You can change your bicolored graph into an oriented surface with boundary. Your cycles become, well, just cycles in this oriented surface with boundary. And then the number of arrows between two cluster variables is just the signed intersection number of the corresponding cycles in your surface. Okay, so don't worry, I'm about to go into more detail about all of this. So if you didn't catch it, you have another chance. So first, let's start with beta underline u and turn it into a bicolored graph. So here's my beta underline, and here's my u. So to turn this into a bicolored graph, I am first just going to draw the wiring diagram of my word beta underline. Okay, and so I'm actually going to draw the braid diagram, which is just instead of having my wires actually cross, I'm going to have the one that goes up cross kind of over the one that goes down. Okay, so here is my braid diagram of B, beta underline. And then I'm going to highlight my hollow crossings, this rightmost sub-expression for U. And then I'm just going to take every solid crossing that I see, so every non-highlighted thing, and replace it with a little white-black bridge like this. So after I've done that, I get this graph. And I add some marked points on the left endpoints for technical reasons, and this is it. So this is the bicolored graph that I get. It's going to tell me everything about the quiver. Okay, so now I need to tell you what about these cycles? So for each solid crossing, each cluster variable, I need a cycle. And okay, so the easiest way to talk about these is to actually define a soap film or a disk that's going to kind of run along the edges of my graph, and the cycle will just be the boundary of my disk. Okay, so what disk is going to correspond to a cluster variable xc or a solid crossing C? Well, it's going to start at a little white-black bridge, and then it's going to cling to the edges that go left from that bridge. So my soap film kind of looks like this. And then it's going to propagate according to these 7 rules. Okay, and this is just best to do an example. So let's start with the disk and the soap film and the cycle for 7. So this disk, it's supposed to start at the bridge, and then it clings to these edges, right? And it goes along, clinging to the edges, and then it hits this bridge 6. And at 6, I see this local situation. So my disk just stops. So that means that the cycle corresponding to 7 is this one, and I orient it this way. Okay, so a slightly more interesting example. Let's see, is the one corresponding to 6. So my disk starts here, it clings, it passes underneath this strand, right? Because that strand is passing over. And then I get to 4, and at 4, I see this situation. So my soap film just passes underneath that bridge undisturbed. And again, at 3, I see exactly the same situation. So my soap film sort of passes undisturbed, and then my soap film continues like this. So in this situation, my cycle is actually a relative cycle. And it looks like that, oriented this way. So yeah, as you see, it's these pictures just tell you exactly what to do. That's how the cycles propagate. And I should say, from here, you can actually tell which cluster variables are frozen and which are mutable. So if your cycle is an honest cycle, it corresponds to a mutable cluster variable. If your cycle is a relative cycle, not an honest cycle, then your cluster variable is frozen. Okay, so I should say, okay, so now you've got the graph, you've got these cycles. You can actually stop here. So if you want to know how many arrows there are between xc and xd, you can just compare the 2 cycles and compute, like how many edges of the graph do they do this on? So how many edges of the graph do both cycles lie on? And if their behavior is like this, well, that contributes a 1 to the number of arrows. If their behavior is like this, it contributes a -1, etc. So you could just stop here and compute the quiver just from this information. But it's a little bit more elegant. It's a little bit more elegant to kind of upgrade the graph to a surface, so you can pull your cycles around a little bit. So how do you do this upgrade? Well, you just take every piece of your graph that looks like this, and you replace it with a little ribbon that looks like this, boundary oriented as indicated. And you take the piece of your graph that look like this and replace it with a different ribbon. So the ribbon is sort of like twisted, so the underside is showing right here. Okay, so if you do that replacement, you get this picture, and then to get your surface, what you should do is you should just collect you should just connect the ribbon fragments along the edges of your graph. And then you should go like this. Okay, so here is the picture of the surface. And now I've drawn the cycles, each cycle corresponding to a cluster variable on top of it. And now, well, the number of arrows between XC and XD is just the signed intersection number of the corresponding cycles on your surface. So if you don't remember the conventions for signed intersection number, that's fine. Let me just in this example, just like as a sanity check. So we see in the quiver, I drew like an arrow from 6 to 7 and an arrow from 3 to 4. And you can check that, okay, there's one crossing between the red and the blue cycle, looks like this. And there's one crossing between the green and the golden cycle like this. And kind of the way it's configured is that the golden cycle and the blue cycle play the same role, right, in these two crossings. If you stare at it closely enough, you can tell this. And so that's why the arrow points in the same direction. Yeah, so let me just summarize quickly what I've told you so far. And actually all I'll tell you because I'm about to end. So our main theorem is that, well, we have these Braid varieties, which generalize open Richardson varieties. And we show that their coordinate rings are cluster algebras. And it's not an abstract statement. We tell you exactly what cluster algebra it is. And to do this, we define some tori called Deodar tori, defined by a greedy procedure. We pick some really nice basis of characters of each one of these tori. They're exactly the functions which define the hypersurfaces in the complement. And then our quiver is basically, well, it's determined by the choices we've already made. Concretely, the way we figure it out is using some determinantal identities, and there's in general type an algorithm to compute it. But in type A, there's kind of even nicer combinatorics where you can draw either a bicolored graph or a surface with some cycles on it, and you can find the quiver from there. Right, and then I mentioned in the very beginning in type A, we also have some interesting relations to knot theory, and in general type, we have some corollaries about the cohomology. Right, and I'll stop there. Thanks so much for listening.
Any questions for Melissa?
What is curious Lefschetz?
Okay, so it is some symmetry among cohomology groups. So if you look at, okay, so let's see, if you look at the cohomology and you look at the Deligne splitting, it turns out that, okay, so you're taking like cohomology indexed by n, and you're now splitting it up into some smaller pieces that are weighted by pairs of integers that sum to n. It turns out that for these varieties, very few of those pieces are non-zero. Only the like QQ pieces are non-zero. And curious Lefschetz says is like, when you're in that situation where very few of these smaller pieces are non-zero, there's some symmetry between, you know, HQQ and H something something, and there's a kind of an explicit isomorphism between these two cohomology groups. And I'm going to refer you to the paper of Lam and Speyer for the exact numbers and the exact isomorphism between those cohomology groups.
Great, thank you.
Can you go back to the slide for the Braid variety? Sort of.
Okay, so I heard go back to the slide about Braid varieties, but did you mean the definition? Okay. Yeah.
Just trying to make sure I am.
Here.
Yeah. So can you sort of? So you gave the dimensions. Go to the next slide. Yeah. Okay. So smooth, irreducible. Okay, so that's good. That's what
Okay, so that list of adjectives was what you wanted to see.
I just,
Okay,
I have a question. I was reading in, I don't know, one of these articles. That's part of the motivation is microlocal geometry. So I'm kind of wondering, like in the special case where you have an open Richardson with computing quadratic polynomials. So I'm kind of wondering if there's any relation to characteristic cycles of Riemann modules. If you can get that from something you're working on.
Yeah, I am not sure. Yeah, I think the context in which I have heard like micro-local is, I think, more of a like a symplectic context. So people who are interested in like Legendrian links, yeah, so maybe I should say the other group, they somehow have a symplectic perspective on this whole thing. And one way to interpret braid varieties is as what are called augmentation varieties for a Legendrian link. And I think that is also related to microlocal sheaves, things like that. But yeah, I can't answer anymore. So sorry, I don't think I know the answer to your question.
Thanks. Other questions from Melissa? If not, let's thank the speaker again. Recording.